All right, so it's a pleasure to welcome everyone here today to the last colloquium for the winter quarter. It's a pleasure to welcome our speaker, Kat Steele. Kat is an assistant professor in mechanical engineering here at the University of Washington. Her research focuses on integrating dynamic simulation, motion analysis, medical imaging, and device design to improve quality of life for individuals with neurologic injuries. She earned her bachelor's degree from the Colorado School of Mines and the MS and PhD degrees in mechanical engineering from Stanford. One interesting thing about Kat is she has worked as an engineer in several hospitals, including the Cleveland Clinic, Denver Children's Hospital, Lucile Packard Children's Hospital, and the Rehabilitation Institute of Chicago. She's been awarded an NIH K-12 Career Development Award in Rehabilitation Engineering and an NSF Career Early Faculty Development Award. So it's a pleasure to welcome Kat, and thank you very much for speaking to us.
Yeah, well, hello everyone. Thanks for joining in week 9 of the quarter. I know that all of your brains must be full of lots of to-do lists, but today I'm going to take you a little bit out of our traditional engineering world and throw you a little bit into medicine and some of the clinical challenges that we're using engineering and design to address to help improve quality of life, especially for individuals who've had a neurologic injury. Now, as a mechanical engineer, all my degrees are in mechanical engineering. You may be wondering what in the world we're doing, spending so much time in the hospital and in the clinic. But I really like to boast to my colleagues, and I know it's corny, but I like to say that I get to work with the ultimate machine. Now, if you walk around the different engineering departments here in EE or ME or CS&E, you'll come across a lot of really amazing machines. I need to update my picture here to Boston Dynamics' latest and greatest, but I still have a soft spot in my heart for Big Dog. But even if you look at some of those most complex machines that we have created as engineers, they really pale in comparison to what I consider the ultimate machine. And I know it's totally corny, but I do see the human body as the ultimate machine. It has so many degrees of freedom. It's an incredibly complex system. You would never build a robot intuitively like the human body, yet it gives us this versatility to perform the many activities of daily life. And to create this complex system, we also have some really amazing components. I challenge you to find a more amazing motor than our muscles. I could talk about muscles all day. They have this beautiful hierarchical structure. They can adapt to whatever forces and loads you put on them every day, getting stronger if you go to the gym, getting weaker if you sit on the couch all day. Also, I challenge you to find any other motor that can fix itself if broken while still operating. Of course, we need a really complex control scheme to control all this, and thankfully we have our brain and our central and peripheral nervous system, which let us organize and coordinate these complex array of motors that we have. And hopefully, probably what you guys are looking forward to after this talk is that we can power this whole system with a really diverse array of fuel sources. And so the human body, as the ultimate machine, as I said, gives us the freedom and the flexibility to pursue all the activities of daily life that we participate in, and that often we take for granted. However, the same complexity that makes this system so versatile, unfortunately, also makes it incredibly prone to disorders due to injury. So whether due to age, injury, or neuromuscular disorders such as cerebral palsy or stroke, even small impairments to the system can greatly hinder performance. And so I spend a lot of my time thinking about, well, how do we understand the movement and performance of this complex machine? And how do we develop better treatments so that we can get individuals back up to optimal performance? And so across the street in the mechanical engineering building, we have our Ability and Innovation Lab. We have a number of different initiatives, and today I'm going to kind of touch on some high level of any of them, but if you want to chat more about any of them in more specific details, feel free to grab me afterwards, or we can grab a coffee. But some of our big areas are, first of all, figuring out how we can optimize orthoses, such as these. Exoskeletons is the new sexy word for orthoses, but they've been around for decades and centuries. Also looking at how we can take some of the technology we use to capture human movement and step out of the lab, step out of the clinic, harness some of these wearable technologies, those amazing sensors that you all are holding in your pockets and on your cell phones, and use those to better quantify and understand human motion. And then also one of our big pieces is looking at how can we better quantify and understand control. how we coordinate this complex movement with this ultimate machine is a really complex problem, not only for understanding how unimpaired individuals move, but especially what happens after you've had a brain injury. And so we spend a lot of our time thinking about how do we quantify these changes in control after brain injury, and how can we use that information to figure out what the best treatment, the best rehabilitation is for each patient. So today, as I said, I'm going to spend a little bit of time in each of those areas, but I'm going to give you kind of a high-level overview of some of our projects and work. But they all address the ultimate machine, whether it's machine diagnostics, understanding how this machine works, machine repair, how can we fix it and make it better, and also a little bit of preventative maintenance. What do we know about how our activities today are going to impact our long-term ability to participate in activities of daily life? Now, in examining a lot of these different areas, today I'm going to focus in on one particular clinical population that we work with a lot, which is individuals with cerebral palsy. So if you're not familiar with cerebral palsy is caused by an injury to the brain at or near the time of birth, and it causes problems with movement and coordination. So as you can tell, that's a pretty broad definition. It's pretty much any brain injury that occurs near the time of birth that happens to impair your motor cortex and hence have effects on how you move and coordinate motion later in life. And so there's many different causes, from infection to blunt trauma to oxygen deprivation. There's a huge range of different causes that can cause this injury near the time of birth. But we see very similar movement patterns and impairments develop as these individuals age. I do think it's important to mention that individuals with cerebral palsy typically live a normal lifespan and have normal cognitive function. So they may move a little bit differently, and our goal is to help them to achieve whatever goals they want to pursue and help them have access to all the activities of daily living. Now, as I said, we often see very similar movement patterns among these individuals with really diverse brain injuries. And today I'm also going to be focusing in on one of the most common that we see, which is called crouch gait. So here you can see a video of a young adolescent male who's walking in a pretty typical crouch gait pattern. Crouch, flex hip and knees, pretty self-explanatory. But as you can imagine, if I made you all walk around like this for a minute, let alone all day, you can imagine that not only is that a very inefficient way to walk, but if left untreated, unfortunately this will lead to joint pain, the formation of bone deformities, and eventually the loss of their ability to walk independently. And so to try to understand not only how these individuals and why these individuals walk the way they do, we also want to have some tools to help us understand how we can improve treatment. And so that's kind of the area that we're going to be exploring today. And in order to explore that area, I'm going to tell you a little bit about our toolbox. We have a really diverse set of tools that we use to understand and quantify human motion. This includes motion analysis. So if you're not familiar with them, most hospitals have clinical motion analysis laboratories where they'll put those reflective balls, which you may have seen from movies like Avatar or pretty much name any other movie with computer graphics, all over the body. But patients will come to the hospital, have those put all over their body, they'll analyze how they move, and from that information, surgeons and therapists will make their treatment decisions. So we use a lot of that clinical data that's currently collected in hospitals. We also use a lot of dynamic modeling and simulation. The human body is so complex, and so by modeling the dynamics, we can get a better sense of how different pieces of the system contribute to motion and quality of life. We also rely a lot on medical imaging to help us peer a little bit underneath the surface, understand muscle structure, muscle function, so that gives us a powerful tool. And from a mechanical engineering perspective, all of these tools are really built upon some of our fundamentals: dynamics, controls, biomechanics. Those are the kind of bread and butter theories that we use to understand and quantify human movement. So first of all, let's just ask a simple question. How do we move? You know, we can walk from point A to point B really easily, but it actually takes a really complex coordination of muscles in order to do that. And so in order to understand how I actually coordinate all of my muscles, does anyone even know how many muscles do I have just to extend my knee? Anyone have a guess? Hold up your fingers. That's a hint, it's under 5. Okay. I saw some 7, some 4. Yeah, there's a 4 up there. So it's called your quadriceps for a reason, quad 4. So even just to extend our knee, we have 4 muscles that we can use to do that. You wouldn't probably never, well, one of you can probably correct me, but you'd probably never design a robot like that. And so when we're trying to understand how we coordinate all this complex muscle activity to produce a really fluid and natural walking motion, one of the tools that we use is dynamic simulation. That's because we can start to understand the role of individual muscles and how they contribute to motion. And that's something that we call a muscle's potential, which we define as a muscle's ability to generate acceleration per unit force. And so, for example, we can look at how do individual muscles support our body? How do individual muscles propel our body? And really, it's all based upon underlying physical principles. If you think back to your physics class, remember Newton's second law, force equals mass times acceleration. This is force equals mass times acceleration. Q is our acceleration. Don't ask me why. But it's a little bit more complex, but that's just Newton's second law applied to the human body. It's a little bit more complex, but just by solving the equations of motion, we can understand a muscle's potential or how all these different actuators are contributing to motion. And so through our simulations, we can understand how do individual muscles actually contribute to motion, and how do those change when we're walking in a pathologic gait pattern, and how might surgeons use that information to guide their surgery. So to create these dynamic simulations, just to give you a little background on the process that we use a free open source software. It's called OpenSim. Anyone can download and use it. It's a NIH-supported software. But we take that clinical motion analysis data that I talked about earlier from the lab, and we scale generic musculoskeletal models that have all the information about where your muscles attach, how strong they are, how much force, how much they can stretch. All that is built into these musculoskeletal models, which we can scale to our individual patients and subjects based upon data from the hospital. We can then perform inverse kinematics to basically match those motions that we have from the lab to how each individual subject is moving, so that our model can recreate the motion of each subject. Now, unfortunately, our systems that we measure human motion are not error-free. So we often end up with what we call residuals. Sometimes it's called the hand of God in the video game literature. But in other words, force does not equal mass times acceleration due to errors in our system. And so we often will do some type of residual reduction algorithm to make sure that force does equal mass times acceleration. And then we often will use a variety of different algorithms to help us understand, well, now how much muscle activity do you actually need to produce this motion or that motion? And there's a variety of different algorithms that we can do that. One we often use is called computed muscle control, but there's a wide variety. But basically, at the end of this process, what we have for a given individual is a full dynamic simulation of their motion and how they're walking and moving, which then we can use to test what-if questions, like, well, what happens if I remove this muscle? Or what happens if I transfer a muscle to a new location, which is one of the common surgeries that we do. And so this gives us a powerful platform to, for example, understand how we control unimpaired walking. So like I said, if we're looking just at how I go from A to B, this is going to give you a quick example of how we coordinate our muscles to do that. Because it is a really beautiful process. Here I'm showing two of your big, powerful muscles in your body. Your vasti, which are a big portion of your quadriceps, and then your gastrocnemius, that big muscle on the back of your calf. And these two muscles do a lot of the heavy lifting for us when we're walking. And these plots right here are showing how each one of these muscles is actually contributing to accelerating your body up and forward or backwards across a walking cycle. So from when my heel touches the ground once to when my heel touches the ground again. And so, for example, you can see that we use our vasti, our quadriceps, to support our body and keep us up early in stance, but also to help brake us so that we're not continually accelerating so that you don't go running into walls. Also, our gastroc, though, it ramps up to both help support and propel us in late stance so that we can keep moving forward. But if you look at these two, there's really a beautiful synchrony where the vasti is really active in early stance and then ramps down, and then the gastroc ramps up to have more activity in late stance. And so this helps to have a really efficient gait patterns where we can use individual muscle groups for multiple purposes, supporting and braking, supporting and propelling us forward. And so that's one of the reasons why human walking is so efficient. But how does this change when we go back to those kids with crouch gait? What happens to this beautiful synchrony that we use to coordinate our muscles when we have a crouch gait pattern? Well, we can look at these same plots for mild, moderate, or severe crouch gait. And what you'll notice is that we have a fundamental change in basically that beautiful on-off synchrony of these muscles completely disappear. As I'm sure many of you would feel as well, as you walk in a deeper and deeper crouch gait. So some of these kids with severe crouch gait walk with up to 80 to 90 degrees, which I can barely do, of knee flexion. But then you have to have your quadriceps on all the time to support your body. And also the ability of your gastroc, that big muscle on the back of your calf to support and propel your body, diminishes once you get into these deeper postures. And so I like to call this driving with your parking brake on, because basically you have to have your quads on to support yourself when you walk in a crouch gait. So, but that also means to support yourself, they're accelerating you backwards. So they're slowing you down. And the further you get into crouch, the more those vasti hinder your forward progression. And so as a result, you need other muscles to compensate so that you can keep moving forward. So muscles like your soleus, another one of those plantar flexors on the back of your calf, have to ramp up in activity to help you move from point A to point B. And so you get this vicious progression of, well, I need my quads on to support my body, but then it's accelerating me backwards, and so then I need other muscles to compensate. And so this is one of the reasons why the crouch gait is such an inefficient gait pattern. And these individuals struggle with fatigue on a daily basis. So this is one example of how we can kind of use these tools to break down this really complex system to understand how do individual muscles contribute to motion, and how can we use that information to help us better understand some of the underlying mechanisms for pathologic gait patterns. So that's an example of a bit of the dynamics, but I guess especially for the electrical engineers, one of the things you all may be curious more about is what about those changes in control? How do we understand how we're actually choosing which of all those muscles to activate to produce a given motion? And unfortunately, this is something that we're not very good at. So all of cerebral palsy, stroke, is caused by an injury to the brain. Every brain injury is unique, so every individual moves slightly differently. And this is a slide that one of the orthopedic surgeons that I work with gave to me. Because this is how he says he feels on a daily basis. He knows that he's trying to address or solve this injury that's caused by an injury to the brain, but pretty much most of the tools that we have available to us are to help us fix the musculoskeletal system. Because we do have lots of secondary muscle tightness, bone deformity, spasticity, effects that impair movement from the musculoskeletal standpoint, but we have very few tools to pull us back and to help us understand those underlying neurologic injuries. And so one of our goals has been to help try to understand how can we find some of those patient-specific parameters that can guide diagnosis and treatment planning. How can we connect the musculoskeletal dynamics, which we understand pretty well, with the underlying neuromuscular control that's required for controlling this really complex machine. Now, it's really hard, as I'm sure you guys have heard multiple times this quarter, to monitor brain activity. It's really noisy. There's some great new ECOG and other technologies that we can use to measure great numbers of neurons. But it's actually really hard for us to understand that underlying central control. But thankfully for us, we do have one other tool available that we can use to understand how the brain is recruiting and activating motion. Does anyone know what this is? Anyone recognize the signal? Besides Matt? I know some of you do. Anyone? Any takers? This is called electromyography. So just like, how many people here have heard of EKGs, electrocardiography? How many people have heard of EEG, electroencephalography? All right, a few more. Yeah, so just like how our heart is another muscle, we can also, whenever our brain sends a message to one of our muscles to activate and produce force, thankfully it produces an electrical potential that we can measure through the skin. And so, for example, and much like EEG, it is, well, it's nowhere near as noisy as EEG. We at least have EEG, but at least gives us insight into how the brain is activating individual muscles. When is it telling a given muscle to turn on and off, and by how much? And so EMG has been one of kind of our baseline tools that's been used in the clinic a lot to try to step back and understand how an individual is coordinating motion. But this is an example of how EMG is currently used in the clinic. We might have a description of how a given patient is moving, something like their knee flexion angle, and then looking at the EMG activity for a few different muscles while they're walking. And this is actually taken from one of the clinical reports. And so you can see that they can see when different muscles are turning on and off for a given patient. Those blue bars show when they should be on and off for normal, unimpaired walking. But basically from this data, clinicians, doctors, therapists have the challenge of figuring out and interpreting this deluge of data about what our muscles is doing. So they have to look at this data and say, well, why is this muscle on? is this muscle on inappropriately? Is it actually contributing to the impaired gait pattern? Or is it just a consequence? If I make you stand like this, your quadriceps are going to be on more than usual. But that doesn't mean that they're contributing to the impaired motion and that I should go and Botox them to basically paralyze them and decrease muscle activity. And so it's really hard to understand why muscles are on. And for the surgeons, too, their question is, well, is it contributing to motion, and should I use this as an indicator to operate? And so a lot of our time in the clinic in the past has been spent looking at individual muscles. But to try to help provide more tools for the doctors to use, one of the strategies that we've been using lately is, instead of focusing on individual muscles, stepping back and instead looking at how we coordinate muscles. And this is through the theory that's known as muscle synergies, or modular-based control of motion. Anyone hear of central pattern generators before? Anyone seen a video of a chicken with its head cut off who's still able to run? Yeah, well, if in case you don't know, a chicken with its head cut off can still run. And that's because a lot of we have these central pattern generators in our spine that can be used to create the cyclic patterns of walking. So whether you're looking at individuals who've had a spinal cord injury also, they can often still produce a stepping pattern. But we know that there's these lower levels of control in our spinal cord that are especially used for cyclic motions like walking. And so muscle synergies are a tool that helps us explore this low-dimensional space. So although I have over 90 muscles in my lower extremities, it's one way to think about it is that could be a 90-plus dimensional control space that I need to figure out how to activate each one of those muscles. But in all reality, we actually have this very low-dimensional space that we work in. If I look at something like walking, it's actually only like a 4 to 6 dimensional space that's used to activate all those different muscles, to control all those different motors. And so we have a much more simplified control space that we actually use for a lot of these activities of daily living. And thankfully, we can kind of look at the dimensionality of this space through the concept of muscle synergies, which is looking at how do we coordinate muscle activity. And we use our EMG data to calculate these synergies. So from EMG data, we can use algorithms like non-negative matrix factorization. If you've heard of principal component analysis, it's very similar. But basically, we can use those algorithms to look at, well, what are the groups of muscles that are consistently activated together? And how complex is this space that we're operating in to control motion? And so in this very simple case, you might have a system of 5 muscles, but 2 synergies, which are these weighted groups of which muscles are activated together, activated in certain patterns over time, can recreate the large majority of the muscle activity that we see during a task such as walking. And so this has been used in a lot of animal studies and human studies in the past to demonstrate that tasks like walking, reaching, balance control, we operate within this low-dimensional space. Now for us, the area that we were most interested in was understanding, well, is there some clinical utility in understanding this low-dimensional space for helping us understand how we coordinate motion? And who knows, could it be used to better control robots, or those are some of the other applications that you can think of. But from prior research, we knew that if you and I, if we have unimpaired walking patterns, we operate in like a 4 to 6 dimensional space for walking. But prior research showed that after stroke, that space is further reduced. So you're in a 2 to 3 dimensional space to coordinate your muscle activity. And so we know that after stroke that these synergies are reduced and that they're related to functional impairment. But the big question that we wanted to know, well, does that also apply to cerebral palsy? Stroke is a brain injury that typically occurs much later in life. You have decades of walking experience, so there it might not be that surprising that you just have this lower dimensional space of what we see in unimpaired individuals. But in cerebral palsy, we have an injury at the time of birth, and so you're growing and developing while you're adapting to your brain injury. And so will we see a similar thing? And so we wanted to look at, well, are these synergies altered in cerebral palsy? And can we use this information to both provide more patient-specific guidance and treatment, and also provide a way for us to improve our musculoskeletal simulations? So just briefly, we did a study of over 500 individuals with cerebral palsy with our partners at Gillette Children's Specialty Healthcare to look at how are synergies in children with cerebral palsy compared to typically developing children. And the short story is, yes, they're altered, and they're altered very similar to what we see in stroke. So here, if I have a given number of synergies, I can look at how much of that variance in all my muscle activity a given number of synergies explains. So like in unimpaired individuals, 3 synergies can usually describe over 90% of the variance in our muscle activity. But if I bring up kids with cerebral palsy with increasing functional impairment, so hemiplegics, diplegics, triplegics, or quadriplegics, so that's just the increasing functional impairment, which limbs are affected, we see that they have this decreasing complexity, where once again, fewer synergies can describe a greater amount of their control space. And so fewer synergies are required to explain their muscle activity and coordination. Now we can also look at, for example, which muscles are activated commonly together. And I won't dwell too much on this, but we can understand which muscles are activated together and how those compare among unimpaired individuals and individuals with cerebral palsy. But the real interesting piece here is that if we look at these synergy structures in kids with cerebral palsy, adults who have had a stroke, or infants, I don't want to encourage too much experimentation with any infants you all know, but if you hold up an infant who's about 1 to 3 months of age and you hold them over a surface and you stretch their hip a little bit, they'll actually produce a stepping pattern. It's called rhythmic stepping in infants. And someone also calculated synergies during this rhythmic stepping in infants. And across all of these, we see this very similar synergistic pattern of muscles, very much like a flexion-extension synergy. So whether after brain injury or early in development, we seem to see a lot of the same muscle coordination across these different populations, which can help us understand what are the strategies that our individuals actually using after a brain injury to control motion. So we've been using these synergies to both understand and differentiate across this really wide variety of brain injuries, to understand more how we can differentiate individuals who have different types of brain injuries and use that information for rehab and training, which I'll talk a little bit more about later. But before we move on from machine diagnostics, I just wanted to mention one other area, and that's motor adaptations. Because it's an amazing thing that our muscles and our bones respond to whatever loads we put on them every day, but it also can be a very detrimental thing. And especially after brain injury, we see significant changes in our muscle properties, and in our bone deformities are also common. And so one of the other areas that we use for diagnostics is understanding, well, what are non-invasive methods that we can use to better quantify changes in muscle properties after brain injury? And one of the tools, looking at more the imaging side of our toolbox that we use for that, is called shear wave elastography, which is a form of ultrasound imaging, where basically if you imagine if I drop a rock into a pond, it'll cause all those ripple waves spreading out to the side. It's a similar phenomena as that, where in the shear wave elastography, we use our ultrasound pulse to cause small vibrations within the muscle tissue. Those small vibrations will cause shear waves to travel through the tissue, and the speed of those shear waves move is related to the material properties. And so we can use that as a non-invasive method to help us understand how stiff are your muscles. If I give you a treatment like Botox, or if we're studying development of early muscle and cerebral palsy, we can non-invasively start to understand how your stiffness and muscle properties are changing over time. So this is an example of an ultrasound image of your tibialis anterior. It's the muscle right on the front of your calf. And this is from a child with hemiplegic cerebral palsy, so where only 1/2 of their body is affected. And so you can see on the affected side, not only is the muscle much thinner, but also you can see that our shear wave speeds, which are by the brightness of those colors, are much faster, indicating that the muscle is much stiffer, as opposed to their less affected side, where you can see that the muscle, first of all, is much thicker, but also we see those slower shear wave speeds. So that's just an example of how we can use ultrasound imaging also as a really nice non-invasive tool to both look at muscle function and development. So that was kind of a brief introduction. Hopefully I didn't overwhelm your guys' minds too much with looking at some of the tools that we use in our toolbox. So whether it's motion analysis, modeling and simulation, EMG, and imaging, we use all of these tools to help us understand that machine diagnostics. How do we move? Why do we move the way we do? But the whole reason that we pursue a lot of these questions is more for this machine repair piece. How can we actually help the doctors and therapists and patients to improve movement after brain injury? Now, if we go back to that example of crouch gait, there are many different treatments for crouch gait. Probably the most common is multi-level orthopedic surgery. It's called multi-level orthopedic surgery because the surgeon will go in and do surgery at multiple levels, so multiple parts of the body all at once. These surgeries can include everything from lengthening tendons, so muscular tendon lengthenings, transferring muscles to new locations. One of the most common ones is, as I mentioned before, you have 4 quadricep muscles. Your top one is your rectus femoris. That muscle is notoriously overactive after brain injury, and so one of the surgeries that they do will be actually removing that muscle from your patella and moving it back to the other side of your knee. It's debatable how well it works, but it occasionally works. But so we have these muscle transfers, and then we also have muscle releases. They also do a lot of bone alignment. As I mentioned, bone deformities are common if you have altered loading on your system. And so they're called osteotomies. They'll cut the bone and rotate it to realign the bones. So these are highly invasive surgeries that they're using to try to adapt the muscles, adapt the skeletal system to help improve movement. Now, there are quite a few different rehab therapeutic approaches, lots of different types of physical therapy, from strength training to like the Locomat, exoskeleton training. There's some new work in electrical stimulation, looking at how we can cleverly, artificially activate the muscles. And also neuromuscular toxins are very common as well. You probably have heard of Botox, which is a paralytic agent, which is also commonly used to try to decrease some of that inappropriate muscle activity. So we have lots of different treatments. However, the challenge is figuring out each brain injury is unique, so what treatment should we do on each individual? And unfortunately, that's something that we're not very good at, and outcomes after treatment are highly variable. So prior studies have shown that after orthopedic surgery, Botox injections, strength training, you name it, unfortunately, only about 50% of the patients have positive improvements in gait, even though that's largely the target of these surgeries, which is about as good as flipping a coin. So we think we can do better. We also recently did a 20-year retrospective study with our partners at Gillette, looking at outcomes there just to see if maybe we were doing better. But this is a common measure that we use, the Gait Deviation Index, or GDI, where a value of 100 means you're walking normal, your kinematics, your joint angles are normal, and each 10-point deviation is one standard deviation from normal. So a GDI of 80 would indicate that on average, your joint angles, your joint moments are 2 standard deviations from unimpaired individuals. And so here you can see for lots of different treatments, the pre-GDI of our different patients, and then the change in GDI after treatment. And so unfortunately, you'll notice where the 0 line is, and we often consider a 5 to 10-point change in GDI clinically significant. And so unfortunately, about 50% of our patients still fall underneath that line. And so we're still struggling to figure out which are the best treatments for each individual. Our overarching goal is to push this up to hopefully help us better identify which treatments each individual should be getting to hopefully give them the best improvements in their walking and functional ability. Now, in looking at this, it can be quite depressing. But one of the things that our clinicians often say to us, if you remember back to that brain and poor praying skeleton I showed you at the beginning, is one of the things that the surgeons say that they have an intuitive feeling is that individuals with good control are more likely to get better. So an experienced doctor might say that if I have 2 patients walk into my clinic and one has good control and one has bad control, I think those patients up high who got lots better after treatment, those are the ones with good control. Any ideas on how you quantify good control? Yeah, it's actually really hard. We'll take any good guesses. So that's a question that we've been working on is, well, how can we help the clinicians and how can we develop tools to both quantify control and then do we see that their intuition that these individuals with good control actually walk better? So for example, let me show you 2 videos. So here we have 2 different patients with cerebral palsy who walk into the lab. Now, if it's easier for you to perhaps imagine them as a robot that you've coordinated and told to control, which one of these would you be prouder of yourself to say, this one has a good control strategy? So I'm going to ask you guys in 3 seconds to point in the direction of which one of these looks to you like it has a good or a better control strategy. So 3, 2, 1. Yeah, everyone's pointing that way. And it's, it looks smooth, it's not jerky, he's got a little bit of arm swing. This is something that intuitively to us feels like good control. Now, if we use some of those traditional measures that the clinicians use, like our GDI, that gait deviation index, we'd see that actually these individuals have exactly the same GDI. Their kinematics deviate from normal the exact same amount. But what we've been looking at, and what I'll show you a little bit more in a second, is we call it the walk DMC, the walk dynamic motor control index. But using those synergies that I talked about before, these individuals are much different in terms of how complex their control is. While this individual has a walk DMC of 100, which is normal, while this individual is more than 2 standard deviations from normal with a walk DMC of about 80. And so we're looking into how we can use these synergies to help us better understand and quantify not just what feels or looks like good control, but what actually is good control. So we did do a big retrospective study of individuals with cerebral palsy who were getting a bunch of different treatments to look at if these measures of synergies, how complex and how high dimensional that space that we're operating in, if it's actually predictive of outcomes after treatment. So we looked at 200 individuals with cerebral palsy who had undergone either Botox, orthopedic surgery, selective dorsal rhizotomy, which is a neural surgery where they actually cut the dorsal roots of the spinal cord. So we looked across all of these treatments to see, can we use synergies and how we coordinate muscles as a way to quantify what the surgeons see as good control. So that's just one example of some of the orthopedic surgery and control pieces that we're using. Now, anyone go to the weight room this morning? All right, no one, it's week 9. Okay, maybe a few. All right, so often another thing that people say to us is, well, what about strength training? Actually, I think I'm gonna skip through this section. It's already 11:20. Basically, strength training doesn't work either. And there's lots of different muscles that we can target. And we've used our simulation to help us understand which muscles would work best. So I think the last part that I'll close on is relating to these orthoses. So you might have noticed this is up here. This is called an ankle-foot orthosis. Most individuals with cerebral palsy and stroke will be prescribed one of these to help improve their walking. But as you can notice, they're pretty simple. However much the orthotist stretches the plastic will determine the thickness of this strut, which will determine how much it can bend. But each individual with every brain injury walks slightly differently, has different walking characteristics. And so one of our goals is to figure out not only how can we use new technologies and additive manufacturing to improve the customization and fabrication of orthoses, but also how can we optimize the properties of each one of these orthoses to each individual's. Of course, there's also lots of fun active exoskeleton, adding motors. We need better batteries is kind of the end of the day of that story. But there's lots of other options with that as well. But so we've been working, not only does UW have a great prosthetics and orthotics program here, that's one of the schools where they train the people who fit prosthetics and orthotics to individuals who've had brain injuries or amputations. So we've been working with them to look at, well, how can we use 3D printing and scanning and other new affordable technology to improve the fabrication of those devices. And also we've been using our musculoskeletal simulation to help us figure out, well, what are the optimal properties? If you're walking in a given crouch gait pattern, what should the stiffness, or if I have an active AFO, optimal torque profile of that actuator be so that I can best improve your energy costs and your walking ability? This is also another place where we can add in our ultrasound. Ultrasound you can use to watch how your muscles are stretching live. Anyone here ever had physical therapy and been required to do stretching afterwards? How many of you actually stuck with your stretching afterwards? Oh, you guys are a very compliant crowd, or you just lie like most of our patients do. So basically, whenever you tell patients to stretch, unfortunately, they usually don't stretch. I'm one of them as well. And so one of our other questions, too, is especially after brain injury, your muscles get tight. And you're supposed to do lots of stretching to prevent those muscles from getting tight, but who wants to do that every single day? And so one of the other things we're looking at with these orthoses is, well, can we cleverly design these and the properties of these so that you basically can stretch your muscles with every step? Can we design the properties such that you don't have to do, even kids with cerebral palsy walk over 3,000 steps per day, so can we use those to help us stretch the muscle? We also have some upper extremity orthoses. These are devices, for example here, this is a device for an individual with a spinal cord injury. Once again, it's been around for over a century and hasn't had much innovation to it. It's called a wrist-driven orthosis. So if you have an injury at about the C5, C6 level of your spinal cord, you can still move your wrist, but you can no longer move your fingers. So this very simple 4-bar linkage-based design, as you flex and extend your wrist, will open and close your hand. And when we were talking with our orthotists over at the UW hospital, we said, well, what is your least favorite orthotic to fabricate? And they said the wrist-driven orthosis. Because if you look at this picture, it's all metal. And how they actually still fabricate this is they actually still pound it out of metal, which can take 13 to 20 hours depending upon your skill level. Now, thankfully, there aren't very many individuals with spinal cord injury, but also it's just a huge burden on time. And so we've had a group of students who've been working on recreating using 3D printing these wrist-driven orthosis to both improve the fabrication process. So now you can just tell a printer to print it for 5 hours and then have 30 minutes to an hour of assembly time. They have a lovely Lego-style manual, even if any of you want to try it out yourself. And also, they've been testing it with locals, individuals with spinal cord injury, and have demonstrated that not only can they add some linkages to get better functional improvement, but also that we can improve some of the thumb function and functionality over these traditional devices. But one of the big goals here, too, is to say, not only how can we use additive manufacturing to make orthoses more widely available and easier to fabricate, but then how can we start plugging in some of the fun, clever new toys that we have? How can we use those flexible electrodes and some actuators to provide an active option as well for individuals who've had stroke or multiple sclerosis? And so there's a lot of exciting things and kind of a stagnation. Prosthetics gets all the attention. I know it's sexy, but orthoses is kind of the neglected, underappreciated brother of prostheses. And so there's a lot of opportunity for innovation in that space. All right, so I think just so that we have time for questions, I'm not going to talk too much about preventative maintenance today, but the big one is just over time, if we leave these gait disorders, unfortunately pain develops and gait deteriorates, and so be nice to your knees because you have that cartilage in there, and it'll deteriorate greatly over time. So before I close today, hopefully I've given you guys just a little bit of an overview of some of the different projects and methods and ways and maybe inspirations, because we do need a lot of EE brain power in all of these projects as well, for how we can use engineering and design tools to improve movement after brain injury. I do also want to mention that I'm one of the individuals who teaches our Engineering Innovations in Medicine class. I don't see anyone in the class here, but this is a year-long design course that we teach for both seniors and beginning graduate students, where you're teamed up with a group of 4 to 5 students, and you work with doctors in the hospital on a wide range of projects. This year we have everything from interventional radiology to gastroenterology. And so if you're looking for an opportunity to dive into the clinic, this can be a great opportunity. Every summer, the doctors come and pitch projects to get the chance to work with you all. And if you're in electrical engineering, there's a pathway for it to count for your senior design class. I think we have 3 electrical engineering seniors in the class this year. So if you have questions or if you're interested in this class next year, you can either take just the fall version, which is a boot camp introduction to medical device design, or you can take the full year-long version where the goal is to create a functional prototype for the specific challenge with your clinical partners over the year. So with that, I want to thank all of my partners. All of this work is done very closely with doctors and therapists, and so we have a big team that works with us, and I'll take any questions that you have. So thank you, guys. Any questions?
I have a question.
Sure.
So you mentioned the importance of getting data from patients at home in addition to their time in a clinic. What are the challenges with home collected data, and what EE innovations could possibly help, or what?
Yeah, so one of, I think, the big challenges is that now we have all these new tools to get data, but more data isn't always a good thing. And so one of the big challenges is understanding how from this deluge of data, and we can now get from lots of different sensors, how we can best make sense of it and distill it into the information that the actual users want, whether it's a doctor, a therapist, or a patient. So that can be one of our big challenges, is just understanding going from deluge to data to something that can actually have an impact on your daily life. There are a lot of interesting security and data transfer protocols, especially as we walk over into the clinic. So if you're using a Fitbit to monitor motion, you don't have to go through a lot of the FDA regulatory requirements. But as soon as you want a doctor to be able to look at some of that data, you have to jump through a lot more, and rightly so, a lot more of the regulatory hoops. But so we do have a lot of gray area now between the things that we can measure at home and making sure that we keep that data private, safe, we do a lot of work on how we can best de-identify to send data across to different centers so that we can get the types of numbers that we need to understand these motion pathologies. But there's a lot of work that needs to be done in terms of both protecting patient privacy while enabling the doctors and the therapists with the information that they need. Here.
Are CP patients born with a normal skeleton, normal muscular, and it's just the signals that are going down that are a little scrambled? So
yes.
Why not try to descramble the signals at an early age?
Yes, and so I think that's the direction that a lot of our cerebral palsy research needs to go. So Eric basically said, well, are these kids born with normal musculoskeletal function? And for 90, I don't know the percentage, but for a big percentage of them, yes, there are some genetic disorders where in addition to having a greater likelihood for a brain injury, you also have some changes in your musculoskeletal structure. But for the wide majority of individuals with cerebral palsy, they're born with normal musculoskeletal system, but the signals that they start to get after brain injury are impaired and lead to a lot of those downstream effects. Now, one of the big problems, and actually is another great one for both EEs and CS, is that we're horrible at diagnosing cerebral palsy. So the average age of diagnosis is still 19 months. And so oftentimes, it's really easy to tell the kids who are going to have severe movement impairments. We know a brain injury occurred near the time of birth. It's all those kids with mild impairments that we have a much harder time to identify. And we won't realize that they have a brain injury until they stop reaching the motor milestones along with all of their peers. And so we do need better, in order to do earlier interventions, we also need better tools to help us push that diagnosis age earlier and help us recognize when there's been brain injuries that are going to lead to, because all babies, if you've watched them move, kind of have these random motions or sleep all the time, and so it's really hard to tell initially who has had a brain injury, who has impaired motion, until later on when they stop meeting the motor milestones that we generally see.
So it seems like from your data, you guys are getting better at the diagnostics areas. Is any group working on a better therapeutic approach to better treat these patients?
Yeah, so that's been a really interesting area, because especially even if you just look at the synergies here. So basically you asked if we're getting better at identifying who's going to respond well to different surgeries. But what about new surgeries or new treatments? And there is a lot of innovation going on. They've tried things like the Locomat and exoskeletons. They haven't really worked too well. So there's lots of things being tried. The challenge is figuring out the ones that are actually going to lead to long-term affordable changes in motion. But one of the things like with Synergies is now we can identify who we think are not going to respond well to any of the surgeries we currently have. But the question is then what do we do with these kids with poor control? And it does open up some new avenues for thinking about, okay, so if we know that they have poor control and they're not going to respond to all of our current treatments, question one is, how adaptable is that control? Can we design a therapy to make it more complex? And two, what are the best methods that we might be able to do that? Or if control is fixed and we don't have methods, and some of the surgeons I work with believe that, they say that someone who has poor control, they're always going to be poor control. That's just something that's set in stone in our nervous system. So if that's the case, given someone's control strategy, what are other methods, whether they're exoskeletons or training to make them move as well as they can, given the limitations in their control? All right. Well, thank you guys for taking the time to dive into the clinic. We need all of your smart brains, so have a good rest of your day.
Thank you very much for speaking with us. Yeah.
Thanks.